What you are about to see, you have probably never seen before in your life. You'll have to watch closely because it will last less than a millionth of a second. That was a strange, new kind of light. Dr. Arthur Shallow is one of the scientists who made that light possible. This is the story of his work on the laser, the light of the future, on experiment. In a flash of lightning are all kinds of waves. You can see some of them as light. Others cause static on your radio or TV set. Lightning is the most spectacular display of what scientists call the electromagnetic spectrum. Scientists have found that the electromagnetic spectrum is a series of waves of varying length stretching over a very broad range. If we let this keyboard represent the electromagnetic spectrum, here's what lightning would sound like. And here's what lightning would look like. This oscilloscope is connected to the organ and reproduces sounds as waves. Here's the whole electromagnetic spectrum at once, lightning. Scientists have not only been able to analyze and measure these waves, but found ways to make some of them very useful. In lightning, these long waves are all jumbled together, but scientists were able to produce, with electricity, wires, coils, and tubes, a single long wave they could control. And we use waves like that today for radio. From the jumble of even shorter waves, scientists were able to produce and control the kind of wave that carries television today. From the jumble of still shorter waves, scientists were able to produce and control the kind of wave that's used for radar and microwave radio relay and many other uses. Up here are very, very short waves, light waves. Scientists have been able to do some amazing things with light, but all the light was still like this, a jumble of waves. To produce and control light like this, in the same way as microwaves, television, or radio, appeared to be impossible. This was a problem that had intrigued many scientists, including Dr. Arthur Shallow, head of the physics department of Stanford University at Palo Alto, California.
Trying to produce shorter and shorter waves had been going on since the early days of radio. When you got them, it wasn't always obvious what you were going to use them for, but they always turned out to be much more useful than anyone could have predicted. So I wondered about even shorter waves. Surely there must be some use for them too. The problem was to find a way to generate light waves in such a way that they would act like radio waves.
This is the way radio waves behave. A series of waves of the same length come from the radio station in step, one after the other. These, of course, are the shadow of water waves, but they act much the same way as radio waves do. Now, the water waves are in step because they're produced by this little bead, vibrating up and down with a steady beat. Radio waves are produced by a tuned circuit in this transmitter. Electricity is alternating in these coils, producing radio waves in a steady rhythm. That's what Dr. Shallow wanted to do, to somehow get light waves to act like radio waves, to get them in step. Now, light waves are out of step because of the way they're produced. If you could magnify what's going on inside that light bulb a couple of million times or so, you'd see how the light is produced by billions upon billions of atoms in the wire. Let's assume this is just one of those atoms. The atom is made up of a nucleus with electrons around it. Some of the electrical energy going through the wire is absorbed by the atom. This causes an electron to jump out of position. The energy is stored temporarily in that electron. When the electron drops back into position, the energy is released as a unit of light. Every time an atom absorbs energy of any kind, an electron is pushed out of position. As it drops back, another unit of light goes out in a new direction. The next time an atom releases its stored energy, the unit of light can radiate out in another direction and would continue until stopped by something. All this happens in a very small fraction of a second. No one knows when a unit of light is going to be emitted or what direction it's going to go. It's spontaneous and out of our control. At the same time, other atoms also are absorbing energy. They radiate units of light out at different times and in new directions. That's why light is out of step. But notice the atom on the right. Sometimes the atoms hold the energy for a longer time, but soon they also emit their light spontaneously. Almost all light is produced by this process. It's called spontaneous emission of radiation. If almost all light is produced spontaneously, like this, how can you get light waves in step?
How light was produced was a theory that was a long time in developing and was the result of the thinking of some of the most brilliant men in science. But the clue to getting atoms to release light in step rather than by spontaneous emission came from one of the greatest minds of the century, Dr. Albert Einstein. Dr. Einstein theorized that when some atoms have absorbed energy, they remain in an excited state for a short time. When an atom releases a unit of light of the proper wavelength and the proper direction, this radiation can trigger other excited atoms to release their units of light. The units of light are added together in step. Each of them can trigger other atoms. The wave would get stronger very quickly as more and more atoms are triggered. Because the atoms are stimulated to emit light, Einstein's theory is called stimulated emission of radiation. Physicists know that stimulated emission occurs all the time, but only in a very small fraction of the atoms. Most of the atoms release radiation spontaneously before stimulated emission can occur. To put Einstein's theory to practical use, some way had to be found to get large numbers of atoms to hold their energy until they could be stimulated to release it in step. Dr. Charles Townes was the first scientist who proved continuous stimulated emission could be achieved. He did it with short microwaves and was awarded a Nobel Prize for his work. I'd known him for a long time. He's my brother-in-law. We had worked together for several years, on and off, whenever we could, on a book, a survey of microwave physics. So I was familiar with the elegant method he used to solve the problems of getting continuous stimulated emission.
Dr. Townes got a good supply of excited molecules, which of course are many times larger than atoms, by supplying energy that was absorbed by ammonia molecules in a gas. Those that released their energy spontaneously were pulled out of the way by an electric field. Those that held on to their energy were piped into a box. When an ammonia molecule released its energy, it emitted a microwave the same length as the box. The microwave bounced back and forth inside the box, triggering other molecules to release their microwaves in step. For the first time, microwaves were amplified by stimulated emission of radiation. So Dr. Townes called his device an M-A-S-E-R, a maser. Already the maser has been used as a molecular clock, accurate to 1 second in 1,000 years, and as an extremely efficient amplifier. If stimulated emission of radiation was possible with microwaves, could it also be done with light, an optical maser? Every time scientists produced waves of the electromagnetic spectrum in step, they did it with a device that was the same length as the wave. So Dr. Townes built a box about this big, the same length as the microwaves emitted by the excited ammonia molecules. But building a box for light waves produced by atoms was much more difficult. The hairs in this paintbrush are a few thousandth of an inch in diameter. More than 100 boxes the size of a light wave would fit inside just one of those hairs. Those were the two problems faced by Dr. Shallow or anyone else who wanted to build an optical maser. Instead of molecules, get a supply of atoms in the excited state and somehow get them to emit their light in step. And find or build a box to bounce the light waves in.
Dr. Townes and I and a number of other physicists began thinking about what had to be done to make an optical maser. From Townes' work on the maser, we knew it was essential not only to get excited atoms, but also to put them in a box that would build up only one wave. It couldn't be like the one he used for microwaves. Such a box for light waves would have to be 10,000 times smaller. During the months we thought about it, it was obvious that we had to consider what could be done with a larger box. Unfortunately, a larger box could sustain not just one wavelength, but many wavelengths traveling in many different directions. I guess what I had in mind, really, from the very beginning, was something like the resonator that had been used in spectroscopy for half a century. Two flat mirrors facing each other. We tried to think of ways to improve this. Then it occurred to me that the mirrors could be far apart. Light from an atom could go out in any direction, but only the light waves that happened to go directly to one of the mirrors would bounce straight back and stay between the mirrors. This would emphasize the waves traveling along the axis. Townes pointed out it would be better than I thought, because after the waves had bounced back and forth between the plates many times, only those that were really parallel would be left. That's how close we collaborated. In the end, our box turned out to be fairly simple. Suppose you had a series of boxes, each one the same dimensions as a wavelength of light. There could be 10,000 boxes, and their total length would be 1 centimeter long, adding up to something you could build. Suppose further that a light wave would travel across the first box. It would be in step when it got to the other side of the box. It would also be in step when it hit the far side of the second box, and the third, fourth, fifth, and sixth boxes. The wave would still be in step when it hit the far wall of the last box 10,000 boxes away. So you would not need a box the same as one wavelength of light, but one long box exactly the same length as 10,000 light waves. Suppose that at each end of the long box there were a mirror. Then the light wave would be bounced back and forth from each mirror, always in step. If one of the mirrors were a semi-transparent mirror, sometimes called a leaky mirror, then some of the light would come out of the box exactly in step. Townes and I were convinced that this was entirely practical. But before it could actually be achieved, something had to be found that had atoms that could be excited as the ammonia gas molecules were in the maser. What was it that had atoms that could be excited and held in the excited state long enough for stimulated emission to take place with light waves?
Dr. Shallow tried to answer his question by looking into the work of other scientists who'd studied light. They had tested thousands of materials, and what they'd found had been carefully recorded and later published. In these tables were the answers to some of his questions. What kind of energy did the atoms absorb? How easily did they absorb it? How long did they store the energy? When they released the energy, what wavelengths of light did they emit, and how many units of light? What atoms could be triggered to emit their light in step? The answer to this question was not there. But the information he found was a start.
I could use this data and make some calculations. Townes, of course, had the maser equations. From the tables and our calculations, potassium seemed promising. We got some potassium vapor lamps, you can buy them, and tried it in the crudest way to see if it would give us a clue. We also considered cesium. By then, we were sure the basic idea was sound. I realized solids had some interesting possibilities. We decided to publish what we knew, and I began learning something about the light given off by solids. One of the first to come to mind was ruby. Rubies had worked pretty well in masers. So I borrowed one and began looking at the wavelengths it emitted. By this time, I was sure an optical maser could be built, but I was not sure I could be the first to do it, and I didn't see any point in killing myself when there was so much good physics to be done. I worked out the physics of light emission from the dark ruby. We decided to publish what we had found out. The red color of the ruby is the result of chromium atoms in the aluminum oxide. Here's how I thought an optical maser using ruby might work. The chromium atoms in ruby could be excited with many different wavelengths of light, from a powerful electronic flash lamp, for example. Enough of the chromium atoms would remain in the excited state for stimulated emission to begin. Some of the light would be lost through the sides of the ruby. But the waves that traveled down the length of the rod would be in step when they came to the fully silvered mirror at one end of the ruby. They would be reflected by the mirror and still be in step. As long as there were enough atoms in the excited state, stimulated emission along the rod would continue to build up energy. As this wave approached the partially silvered mirror at the other end, a good portion of the light would go through the mirror and continue as a powerful beam of light. The rest of the light would be reflected, and stimulated emission would continue if enough atoms were still in the excited state. The beam of light that developed in the ruby rod should build up very quickly because atoms would be triggered to give up their energy faster than they would spontaneously. It should be a highly directed beam because only the waves moving along the length of the ruby rod would be amplified. All the waves in the transmitted beam should be in step because stimulated emission has triggered them all in step.
This information about the theory of an optical maser and dark red ruby as a suggested material was made available to other physicists in published papers, and the race to build one was on. Within a year, the first optical maser using a pale pink ruby was built by Dr. Theodore Maiman. The new device for light amplification by stimulated emission of radiation was soon called an LASER, a laser. In the few years since the first laser, they've been improved many times. This laser in Dr. Shallow's laboratory is a new tool he uses to continue his investigation into the physics of the world around us. He and John Emmett, a graduate student, are setting up the laser, getting ready for an experiment. Those two tubes will flash light energy that will be absorbed by the chromium atoms in that ruby rod. The parallel light from the ruby will bounce back from this special mirror through the ruby to this leaky mirror. Some of the ruby light will bounce back through the ruby but at the same time, a powerful burst of laser light will pass through the mirror to the test target, a black photographic print. The power to flash the tubes is now ready. The laser is about to deliver 200 million watts of power. Where the laser beam struck the test print, the coating is burned away. Now they know the laser beam is aimed properly. The liquid in that tube is moved into the same spot. The experiment is now ready to begin. The laser beam has subjected the liquid to enormous electromagnetic stress. The knowledge they're seeking is the knowledge of the future, made possible for the first time because of the light of the future. And it is the light of the future because it's a new kind of light. The flash of some lasers can occur in an incredibly short time. This number is changing once every second. This is changing 10 times a second. This one, 100, 1,000, 10,000. This one is changing 100,000 times a second. Each flash of some lasers lasts about 100 millionth of a second. That's 1,000 times shorter than one of these flashes. In that incredibly short time, the laser can deliver a tremendous punch. Behind this sheet of glass are 2 nails and 2 rubber bands. Let's say they represent the energy delivered by 2 units of light. Then this represents 10 units of light added together and delivered at the same time. To illustrate the actual energy delivered by a laser beam using rubber bands, you'd need millions of rubber bands tied end to end and millions of strands of rubber bands, all releasing their energy in a millionth of a second or so. That's why the laser beam delivers such a powerful burst in such a short time. Now, this is ordinary, mixed-up, old-fashioned kind of light out of step. With a lens, it can be focused to a small spot. The energy in the ordinary beam of light is concentrated in that spot. Because laser light is so parallel, nearly all of its energy would be focused to a spot thousands of times smaller than the point of a pin. The energy concentrated on that tiny spot can result in heat 1 billion times hotter than the surface of the sun. The laser beam has great potential in communications. Here's one reason why. These thick rods represent long waves. These thin wires represent very short waves. In communications, the waves have to conform to the information you want to send over them. Notice the long waves conform to the large variations. The very short waves conform to the same variations as the long waves, but in addition can carry the small variations the long waves missed. The shorter the waves, the more information they can carry. The light waves in a laser beam are so short, one beam could carry all the telephone calls, the radio programs and television programs in the whole world at the same time. No wonder the potential of laser light has excited scientists and engineers. By now, they've developed lasers using other solids and liquids and gases too. Remember Dr. Shallow said, no one would be able to predict what the shorter waves would be used for, but they always turned out to be more useful than anyone could have predicted?
The laser for communications has great potential, but there are still some problems. All 7 New York television channels have already been carried by one laser beam at the same time, as a test. Laser beams would work very well outside the Earth's atmosphere. Our astronauts have been experimenting with the laser during space flights. Because the beam can be focused so sharply, it can conceivably be used to communicate with someone on the nearest star. Because the beam can be focused to such a tiny spot, it has been used to investigate the submicroscopic world. The intense beam produced by the laser can generate heat considerably hotter than the surface of the sun. Holes can be burned in materials that are highly resistant to heat. Medical and dental use of the laser has promise. Fortunately, the amount of energy in a laser beam can be adjusted to deliver a delicate touch as well as a powerful blow. Some people doubt the laser will be practical, in an economic sense, for many years to come, if at all. But research on the laser is moving at a rapid pace. Within 4 years after the first laser, 1,000 scientists from 20 countries attended a conference on laser problems. No one can foresee what 1,000 inquisitive and imaginative scientists will come up with. I'm interested in what we can do with the laser as a new tool, to find out new information about physics. The knowledge we're seeking is really knowledge of two kinds: how things behave and how things can be made to behave. In the case of the laser research, the whole historic background indicated if you could get light waves in step, there would be some use for them. I don't think anyone should be restricted from the pursuit of this kind of knowledge. The many difficulties that seem to stand in the way of using this knowledge will be swept away later by somebody else.
This knowledge has given us radio, television, microwaves, the maser, and now the laser. Scientists still haven't found ways to get all the waves in the electromagnetic spectrum in step, especially the waves at this end, the shorter waves. And there are shorter waves yet, beyond light. But the fact that now, for the first time, light waves can be produced in step with the laser means scientists have a new tool to continue this search. Dr. Shallow, building on the work of other scientists, has added his own contribution to our understanding of how light behaves. His idea of how light could be made to behave has given us the laser, a new tool for experiment.